Take a close look at these three people. Examine the texture of the hair, the fall of the light, and the way the skin creases. Which one of them is actually real? None of them. Every face on your screen was synthesized from scratch by an artificial intelligence. In traditional supervised learning, an AI acts as a digital cataloger. We provide millions of images labeled by humans, and the machine learns to recognize the specific patterns that define a category, like a face or a car. Modern unsupervised learning models operate differently. Instead of relying on human labels, these systems are designed to identify the internal rules and patterns of raw data on their own. By modeling a dataset's underlying probability distribution, these systems can move beyond recognition to generate entirely novel samples. They learn the mathematical likelihood of where a pixel should be, allowing them to invent data that follows the same rules as the real world. To bridge the gap between identifying an object and creating one, computer scientists developed two distinct architectures, each operating on a different mathematical philosophy. The first path relies on latent variables. These are the invisible parameters that define a dataset, the specific tilt of a head, the shade of a skin tone, or the exact hair color. A classic autoencoder finds these variables by forcing an image through a mathematical bottleneck. It compresses the data into a dense vector of representative features. Then a second network tries to reconstruct the original image from that tiny fingerprint. However, a standard autoencoder is deterministic. Because it maps inputs to fixed points, it can only reproduce what it has already seen. It memorizes existing data, never creating anything new. The Variational Autoencoder, or VAE, solves this by turning that bottleneck into a probability distribution. Instead of a single point, the model learns a range of likely values. This creates a continuous latent space where every point represents a valid output. Because the space is smooth and has no gaps, the AI can sample any random coordinate to generate a brand new, coherent image. This provides a specific interface for generation. By isolating one variable, like head pose, we can adjust it while the rest of the image, like identity or background, remains unchanged. VAEs act as a structured control board for reality. They give researchers the ability to manually tune the underlying variables that govern a synthetic generation. But there is another way to generate data. What if we stop trying to organize the variables and focus entirely on creating results indistinguishable from the real thing? This is the logic of the Generative Adversarial Network, or GAN. It is a system built on a zero-sum competition between two different neural networks. The generator is the first network. It transforms random noise into a synthetic imitation of the training data. The discriminator is the detective, comparing this work against authentic examples. If it detects a discrepancy, it flags the forgery, forcing a retry. This creates an arms race. Each time the discriminator patches a fake, the generator learns to improve its output. This continues until the forged data is so accurate that the discriminator can no longer tell the difference between synthetic and real. This adversarial approach has evolved into tools like GANs. By linking systems together, researchers can translate styles across domains, like converting a video of a horse into a zebra while maintaining the original movement. Researchers also use this method for high-fidelity voice cloning. By analyzing audio spectrograms, a GAN learns the unique frequency and cadence of a specific speaker, allowing it to synthesize speech that matches the target's voice. GANs produce these results not through a careful understanding of features, but by optimizing a generator to successfully defeat a dedicated discriminator. Whether an AI is compressing data or training through competition, it is ultimately mapping the statistical distribution of the world around us. Once a model understands these distributions, it can simulate reality. Autonomous systems use this logic to generate rare, dangerous outliers, like a pedestrian suddenly appearing from behind a car, to train their software before it ever reaches the road. These generative foundations are currently driving breakthroughs in drug discovery, adaptive robotics, and digital media. We have moved past teaching machines how to look at our world and have finally given them the tools to dream up their own. If you want to dive deeper into the neural networks and the mathematics of the modern AI landscape, join our community. Follow Learn by Doing with Steven, Sunang Shengzhi, as well as Steven Data Talk and Steven Shuju Nantan on Xiaohongshu, our official WeChat account, YouTube, and Spotify. Check the show notes for the Linktree URL at linktree.ee/learnbydoingwithsteven to subscribe and continue your learning journey.